Everyone, this is Rebecca Arvin with the Water Environment Federation. I want to welcome each of you to the Case Histories on the Use of Peracetic Acid webcast, sponsored by the FMC Corporation. Before we begin, I would like to quickly review a few logistics. All of the PDF PowerPoint presentations are available for downloading at WEF's FTP link. This link was distributed via email yesterday and will be distributed again tomorrow for anyone that registered after the time of distribution. The FTP link for this webcast also has information on how to receive professional development hours for those eligible to receive these training credits. There are 2 PDH credits for this webcast. You will need to complete the evaluation form to receive the PDH certificate. Your feedback on this webcast is important and helps identify future webcast topics that are timely and helpful to you. Please follow the PDH instructions and check with your state accreditation agency on how to receive this credit. During this webcast, while you cannot speak directly to the presenters, you will, however, have an opportunity to submit questions by typing in your specific question via the pane that appears on your PC. Today's moderator, Gary Hunter, will be accumulating questions and direct them to the presenters at the end of the webcast. We will be recording this webcast. A link will be sent to all registered users tomorrow so that you can share it with other colleagues who could not attend the webcast. If you have any additional questions after the webcast is ended, please email webcast with an S at wef.org. Before we get started, I have a poll question for everyone. Let me go ahead and launch that. The question is, how many people are participating in the webcast today at your computer? If you're participating by yourself, just respond 1. If you're participating in a conference room, for example, if you could do a quick head count, that would be great. And I'll just give that a few seconds for everyone to get their vote in. All right, thank you so much, everyone. I'll go ahead and share those results. Looks like we have about 83% participating by themselves today. So thank you for that. I would like to thank Gary for moderating today's webcast. Gary Hunter is a senior wastewater process engineer with Black & Veatch. Gary?
Thank you so much, Rebecca. It's a delight to be able to be with you today to share with you this webinar on the use of peracetic acid. We have brought together individuals from both the vendors and end users of peracetic acid to share with us their experiences and their opinions and thoughts on the application of peracetic acid in the wastewater industry. This webinar is an outgrowth of a session that was held at the Disinfection and Public Health Specialty Conference last year relative to peracetic acid, as well as a session at WEFTEC on peracetic acid. So today's speakers will be Bob Freeborn from Peregrine Solutions, Alberto Gabarli from FMC, and Glabra Skip from the city of St. Augustine. Do I have the next slide, please? Bob Freeborn will be our first speaker. Bob is a sales vice president with Peregrine Solutions. He's a bachelor's in chemistry from State University of College at Buffalo. He's worked over 17 years in sales and marketing in the specialty chemical industry. He has over 35 years of experience in all areas of water treatment for both municipal and industrial applications. Bob is leading the effort with Peregrine and has spent the last 2 to 3 years dedicated to study, completing over 25 different studies personally, looking at the application of peracetic acid in not just the wastewater industry, but in stormwater and CSO and other applications. With that, I'd like to invite Bob to make his presentation.
Thank you, Gary, and thank you, Rebecca, for this opportunity. First off, I'd like to bring everyone up to speed what peracetic acid is. I've given a lot of speeches on this, but basically there's 3 different acronyms: PAA, peracetic acid, or proxyacetic acid. You can look up each one, you can Google it, and you'll find out a lot of details about the product. Basically, it's an equilibrium reaction between hydrogen peroxide, acetic acid, and water. Peracetic acid is formed after a 4 to 5 day curing process. Heat's released, and what occurs is an equilibrium at different percentages. You can have 12%, 5%, 18%. Originally, they were starting at 36%, but found it was very unstable. For the municipal industry, it was found that 12 to 15% or 16% was a good product mix. It gave you the ability to feed at lower volumes and was applicable to municipalities. The food and beverage industry uses about a 5% mixture. What does the killing is the OH group on the peracetic acid. So that's very critical in maintaining that balance. If the peroxide is depleted, the shift goes back to acetic acid. So it's very, you have to understand what the dynamics are and why it's important to maintain peracetic acid levels. Now, the difference between PA and chlorine bleach, I had a very busy slide originally, but I've gotten it down to about 5 different key points. PA is a green product. When it finally breaks down, the breakdown products are acetic acid and water, and finally carbon dioxide. The only thing you can find trace amounts would be organic acids in the water. But all my tests, as soon as I see it hit a discharge stream, basically the PA is gone. It reverts back to acetic acid. As compared to chlorine bleach, where they're carcinogenic, mutagenic byproducts. You can go to 6 times lower dosage, which means lower volumes, lower pump sizes, lower storage containers. Chlorine bleach, you may have to have high residual chlorine for available free chlorine, which does the killing. This means you could, instead of a 5,000-gallon tank, you need a 100,000-gallon tank to store chlorine bleach. There's no need to deactivate. Again, the studies we've shown shows that within 15 seconds, you cannot detect the product in the discharge stream. Now, this is important when you start taking a look at the regulations and the toxicity of the product. With chlorine bleach, you may need dechlorination. It depends how low. Some of the states are 0.034, 0.038. I think some of the new regulations are 0.01. So you definitely have to dechlorinate, but you still have byproducts available. PA is not affected by ammonia organics as compared to chlorine bleach, which will degrade, and you'll have a break point that you'll have to reach with chlorine. We have also found in a very, very detailed study that it's economically viable versus chlorine and dechlorination. With the dechlorination process, that typically is the controlling factor, which you'll see very high costs. Could you please flip? All right, the next slide I talk about the PA concentrations over time and temperature. You'll see on the top graph that the 59 degrees, 77 degrees, you see very, very little degradation of the product. What does degrade is the oxygen off the peroxide. Again, shifts equilibrium. So if you test PA, you'll see the PA drop because of that, not the PA degradation. When you take a look at sodium hypochlorite in solution, the high temperatures, and this is right out of White's handbook, you will see degradation over time. Studies I've seen over the past 2 years locally, they've lost up to 50% of a 12% concentration in less than 30 days. So this is important in CSOs or applications where you don't use a large volume, but you have higher temperatures. So this is very critical. Can you flip? Our next slide, pretty simple slide, PA is PAA. If you remember, I talked about 12 and 15% concentrations. I've done side-by-side studies with Solvay's 12 and 15% PAA in the field applications. The data we've returned demonstrates there's zero impact between 2 different concentration levels for rate of reaction or efficacy. Now, we want to a step further. The customer that was applying this, I left the facility, he ran the study, and he verified the same results. If anyone's interested, I have his name and phone number. He's more than willing for you to call him and talk to him about the study he performed individually without me there. Next slide, please. Now, just to let you know that PA isn't simply applied, you put it in there, it kills the bacteria or pathogens or viruses. There's a lot of other factors that influence the reactivity of PAA. The way we approach a facility is we want to know what the incoming chemistry is of all the waters coming into the facility, what impacts that, what are the hydraulics of the facility, what's the design criteria, what's the design maximum parameters that we have to work with, but then also, some the other things, are there reducing agents that may be in the water? Is there a background issue? Are there solids? Do you have solids carryover? Is there a lot of iron that comes in? Are you a high manganese area? Those are key factors in determining what your dosage of PAA will be. But if you take a look, the demonstrations we've looked at so far over the past two to 3 years is normal secondary treatment. As long as the facility is running good, less than 10 parts per million of solids, you can typically predict what the dosage will be in that facility. But then you take a look at some other places. If you have marginally performing UV systems, this can enhance the performance of the UV. We've seen places where UVTs drop, and by feeding PAA, you meet the permit levels, and you can discharge the water. Another thing we just found is that a lot of the landfills are providing leachate to the waste treatment plants to get rid of them. So they have huge leachate issues. They may dump all at once. They may feed at 100 gallons a minute. What this does, it causes a huge demand because it's a reducing agent. It will kill the PAA. Very similar. Sodium bisulfite will kill chlorine, as it will kill the PAA. So you have to understand, if you're feeding leachates, what is the background? One thing we're looking at is having to feed a sacrificial oxidant to overcome that demand before the PAA can do its job. So again, you have to understand all the dynamics involved in this process. It's not simply just applying the product and saying, okay, we're going to get the kill. Another one is we had a requirement in Florida, non-detect fecal. We were able to achieve those goals. Now, it took a lot of testing, a lot of work to try and apply it at the right place, but we could achieve non-detect limits. Another thing we've looked at recently is bypass and redirect conditions. Some of these facilities don't have the ability to hold water, so they have to bypass the plant, or in New Jersey, they call it redirect. At that point, we actually bypass and redirect around the secondaries and filtration and UV. The tests we've conducted, we can handle that discharge and still maintain compliance. We've also seen secondary clarifier solids carryover. I'll show you 2 charts later that demonstrates this and what the forgiveness of PAA is. Filter fouling. We're finding that this will take care of the organics and slime layers that build up in filters. You can also use it for filamentous bulking. We've seen that in troughs where you can reduce that. You could also put in your recycle stream. Quite a few people use chlorine bleach right now for that. Snail fouling. This is something that we found in New Jersey. It'll clean the lines out. It'll clean all the equipment out. Snails do not like PAA, and they're going to find a way to get away from it. You'll see snails climbing the walls to get away from the contact with PAA. Lagoon overflows and stagnation. This is key in some of the places in Missouri and small, 50,000 gallon per day facilities where they have lagoons. Stagnation is an issue. You have to understand what the components are, how it changes from day to day. So you have to be building that into your equation. Aquifer reinjection, that's pretty self-explanatory, a lot of work down in Florida. Reuse reclaim, a lot of the work that Solvay did was over in Italy and Milan, and that was primarily the use for the waters to spray it back on the crops. We found also recently in New Jersey, we've looked at biphenyl and dioxin separation from sludge. They're finding that it's very favorable, so we're doing extensive studies on that. The last one is algae control and launders. I'll show you a picture of one of the facilities, and I don't have an after picture, but what it did, it cleaned all the launders up. It also cleaned the overflow of weirs and kept the algae from growing. Next slide, please. And also, we're looking at a lot more CSO applications. In this, you're dealing with pH issues, solids issues, isolated locations. They may be, 1,000 yards to a mile away from your feed point. And a lot of them also have flow exceedances. They overflow. We have problems with how do you control it, how do you maintain it, and how do you automate it. A lot of these places you can't get to. So those are some of the challenges. But I just want to let you know that it's a full process approach, not a simple feed the chemical, get the kill. You've got to intimately understand the process from beginning to end, what the cause and effects are throughout the entire process. Next slide, please. Now, the field demonstrations. Over the past 2.5 years, we've represented Solvay Chemicals, who produces the product. They're out of Belgium, but they have a Houston office. We've conducted over 25 lab evaluations to date in 11 states. Now, one thing about lab evaluations that you have to understand, I've done each and every one of the ones we've conducted. Every time I run a lab evaluation, I can almost guarantee I can go out to the facility and cut the dosage in half. That's important because lab studies that have been conducted over the past 10 to 15 years go at high dosages. I've read studies, I've got 50 papers that show me anywhere between 2, 4, 8, 10 parts per million in secondaries. Well, what I'm going to show you a little bit will kind of blow all that out of the water. I looked at the lab studies, and in every application I've gone to, either side stream or full scale, I'm exactly half the dosage of what I found in the lab. Reason for that is you're using a dilute solution, a PA for lab studies, versus feeding it neat. And that's one of the key points at the end. Side stream studies, 3 to date. That's the bypass and the redirect. Full-scale evaluations. We got 5 of them that we've conducted, and we have 6 more wastewater and 4 CSOs coming up. Active accounts right now combine CSOs, redirects, reclaims, and waste treatments, 5 active accounts throughout North America. Next slide, please. We'll talk about some the actual field results. So the charts and graphs you see here is their data collected at Steubenville, the original study from March to July 2012. First thing is that we tracked, the Ohio EPA required us to track PAA levels and flows every 2 hours during the entire study. The data we have throughout the entire study every 2 hours for over 3 months. So we have quite a bit of data to understand what the reaction is, how it flow paces, and that was one of the keys of the Ohio State wanted flow pacing. Now this chart here was interesting. Like everyone else, everyone wants to control costs. Well, what we did is we went into the study at 1.5 parts per million, and we started tracking our PA residuals, which is on the right-hand column. Left-hand column are fecal coliform levels coming from the that are being discharged. Okay, that's out of the chlorine contact chamber. So we started off at 1.5 parts per million. If you look for the 5 to 7 days, we're down almost to single digits. It's so low that, the summer limits that we're achieving was 200 CFUs per 100 mils or less. We're down to single digits. Well, the superintendent said, look, I want to see how low I can turn it down. So independently, he started turning the pump down. And you look at days 7 to 9, he was getting it down to where we finally hit residuals in the discharge of 0.2 to 0.21 parts per million. But look at the fecal levels. They jumped up to 1,000. So it was obvious that there's a bottom floor to the product. So what we did is he started increasing the pump slowly. We start changing it daily and every couple hours to see what the impact is. Once we started achieving about a 0.3 to 0.4 part per million residual, all of a sudden our fecal levels dropped down below the 200 limit and stayed there for the duration of March. So that's key, because what it shows you is you can dial the program in. It also shows us that there is a bottom floor to the product. If you go any lower, you will increase. You can have E. coli and fecal levels. I see that normally E. coli and fecal track one another, and Entero's a little slower in what the kill rates are. But you will see that there isn't a direct relationship to PA residual levels in the discharge and the fecal levels. Next slide, please. This is a diagram of the actual contact chamber in Steubenville. It's a little busy, but I'll kind of guide you through it. The secondary effluent comes in from a single pipe from 3 clarifiers, hits a head wall, splits off, and immediately goes into 2 channels down to the end. It's a typical serpentine, goes back, and finally goes to the far end, discharges through a weir, and directly to the Ohio River. It's about a 25-foot discharge line that goes to the river, and I'll show you what the flume looks like going to the river. But this is key because the flows coming into this facility are typically 7 to 8 million gallons per day. It maxes out at 13 million gallons per day. Then they have to go to bypass, which we've seen flows up to 30 million gallons a day. So we had to treat all that water going out to the Ohio River in less than 9 minutes. That's key here because once you have a rainfall and you have that much water coming to the plant, we have to go to bypass and we have to meet discharge limits. To give you some numbers on the latest discharge, we were seeing about 690,000 fecal, 100 CFUs per 100 mil fecal limits In 9 minutes time, we got down to 440. So the kill is very effective. How it's applied is key. And again, knowing the hydraulics. We worked for 6 months to improve the hydraulics, make sure you put the right weirs in, the dams, the gates, and then we started the trial up again. So again, there's a mixture. 90% of it could be mechanical and 10% the PAA. But there is a balance between the two. Next slide, please. This shows the same chamber, looking at it from the south, and you see up at the top there's a grating. That's the head wall. You can see on to the right side is where it splits. The first chamber comes back down the second in the middle, and then back down the third. I want to show you that because of how clean the walls are. This was on PAA, and you don't see any slime in the system. Next slide, please. When we first set up, it was ordered through the Ohio EPA that we kept it contained. Again, we tried to maintain it so that we're feeding directly at that application point. Our application point was 25 feet ahead of the head wall. The pipe made a 90-degree turn, and in 5 seconds' time from adding the product to the head wall of that chlorine contact chamber, we got 25% reduction in fecal levels. That's how fast the product works. And that's one of the keys. When I close here, I'll explain how that's key to this. But if you see, it's a very simple system. We're feeding out of totes. Our pump was in the doghouse on the left. We fed 25 feet ahead, and we flow paced the pumps. That's all that was required to run the evaluation. The state came by. They approved the application because of the way it was contained over the basin, and we fed the product and let it flow pace based on north and south contact chamber flows. But again, you don't need elaborate feed equipment. It's very simple to apply. The key is keep it simple. I know there's all sorts of complex monitors, controllers. We've tested a bunch of them. I'll go through some of the data we've seen with some of them, and another story about Steubenville, what we saw with one of the monitors. Next slide, please. This is the overflow where I was telling you about. This is before we use PAA. You can see the slime layers that have built up on the algae on the overflows, but that goes directly out to the Ohio River. It connects up and goes down a pipe and discharges. So that was before. What we've done is when the PA levels are 0.3 to 0.4, that overflow weir is clean. There's no buildup of algae at all. Here's the discharge. You're looking straight down from that discharge, the overflow, directly into the Ohio River. This demonstrates where the plume goes out into the river. I'm going to give you some interesting facts here of what we found. For about 25 feet out in the Ohio, there's absolutely zero flow. The plume went straight out into the river until it finally hit the flow downstream. Then it made an immediate right and took off. So what we wanted to do is, one of the criteria from Ohio is we had to pass the acute wet test. So we grabbed samples, we did the proper wet tests, we had labs come in and do it all, but we also wanted to see what the total chlorine residual, which is the same test you would use for PAA with a different multiplier, but see what that is in the plume and outside of the plume. Well, we tested the plume, and it was very similar to what we saw, 0.3 parts per million. We went 25 feet upstream and got 0.25. We went out into the middle of the Ohio in a boat and got 0.3. So that's important here, because what it shows is now we're dealing with a background in the receiving stream. Is it interference? Is it actual halogens that we're testing? There's a power plant upstream. There could be brominated products that are part of that. We didn't have enough information to test it, but we did see the receiving stream had a background TRC level that we had to take in consideration. That's important when you take a look at acute levels too, because you've got to understand the background that you're dealing with and how the toxicologists and regulators would put a limit on what our discharge is. I've done further studies to show that as soon as it hits the water, all right, we took discharge streams from the Mississippi and also in Kansas City, I ran tests on that, and in 15 seconds time, the PAA hit the background level. It was gone. You couldn't test it. So again, that's how fast it dissipates in the environment. So those are some of the problems we're going to have, bringing this out is how do you limit it? How do you put regulation on it? How do you put limits on discharge levels. So those are some of the key points. Next slide, please. Again, what we did here is plot out our normal curves, our geomean fecal levels on the left, and then how when we finally hit a 0.3 to 0.4, how they went down to 100 CFUs or less. Again, these are standard charts you'll find in a lot of the documents. That dosages are much lower, though. A lot of places you'll see 2-3 parts per million achieving these same curves. This is actual data from the facility, and again, we took 3 to 4 tests a week, and plus we were tracking PAA levels and flow rates for over three months. Next slide, please. Now, this slide is a little busy, but the next slide will leave me busier. We were running along in June of 2012, and the summer limit's 200. And what we found is that all of a sudden the secondary clarifier burped. We got up to 52,000 CFUs per 100. We don't know why it burped. We saw solids carrying over. We're concerned, okay, what do? Do we increase the PA levels? We just let it ride because it was flow pacing. We started taking tests. We never changed the dosage. Okay? Now, I want to let everyone know the dosage we're feeding here with 2,000 to 9,000 CFUs per 100 mils coming out of the secondary is 0.75 parts per million of PAA active. That's all. We never changed the dosage during this burp, and you can see on the right-hand side, we met the 200 limit for the summer levels. So at this point, that shows the forgiveness of the product without having to change dosages. Chlorine, you'd probably have to start changing dosages to get the same impact. Next slide. Now, they were working on the clarifiers in the summer 2013. In May, they were shutting one down. They were repairing one, running two. They put new scrapers in, new internals, and they had problems maintaining their sludge bed. All of a sudden, out of the blue in the 8th, we got 290,000 counts. On the left scale, you can see 290,000. Well, guess what? Never changed dosage, 0.75 parts per million. The flow pacing maintained that rate. They kept testing. They did a lot of tests to see what the residuals were. Actually, the residuals dropped down to a 0.1. It was consumed completely. But what happened is we never changed dosage, never went out of compliance. And as soon as the level started dropping back down, our discharge limits dropped down to 100, 120, 110, back down to the normal double-digit levels. So again, you talk about forgiveness. It doesn't take much PAA, the active, to kill pathogens. Now the key is it takes a lot more to overcome reducing agents, solids, other things that impact the performance of the product. Next slide, please. Now, I'm going to close it up here. You can see that the way we approach it is from a complete plant perspective. You got to keep the dosing and feed systems simple. All right, not cookie cutter. What's interesting here is that I'm going to tell you a little story about Steubenville. I think everyone's experienced some cold weather lately. Well, about 3 weeks ago, they had real cold weather. They got ice on their sonic flow meters on the discharges, and they weren't usable. So now they didn't know how to flow pace. So what they did is they reverted to the online monitor we have that's in the water. For 2 days, used that as the controller. Now, there's a differential there. We found out what the difference was, but they used the monitor as a controller and kept them in compliance. So again, you can do it. There's a lot of work being done now in online monitors and online analyzers, and they're really moving a lot further than what normally was out there in the market. Next thing, every application is unique. I go and see every single facility before we even attempt to feed. Some places we've walked away from. Places in Pennsylvania with high manganese levels will be extremely hard to treat. They've looked at fracking. The problem with fracking is you use so much your pH drops down to 2 to 3 in your solution water. So that's really not an applicable application. So again, you've got to understand what the impact is and what the effect is. Flow pacing has to be done. It's highly recommended. If not, you can use a controller or a monitor. But again, I would prefer doing flow pacing. It's extremely forgiving. You can see the levels, 52,000 to 290,000, never change dosage. The key here is you have to feed it neat. Forget using mixers, forget using dilution water. The key is when you have a 12 and 15% solution, you're feeding it 120,000 or 150,000 parts per million at that point source. Again, in 5 seconds time, we saw a 25% reduction in fecal levels. That's how fast the product works. Then what you do is maintain the residual and give it the holding time to get the rest of the kill. Right now, we're recommending passivated stainless tanks and feed through stainless tubing. You take a look, that may be expensive up front. You're using smaller tanks, you're using tubing, smaller pumps. If you're putting a new installation in compared to chlorine, it will be cost equal or less based on the footprint. You may don't need the footprint for cement. So again, you keep it simple. Polyethylene, HDPE, fiberglass, the PA acts on the plasticizers and will soften it up. Okay, you will be replacing that material. To date, we've tested hundreds of products with Solvay's research folks and also outside suppliers, and have not found anything other than stainless that will hold up and give you the safety and security that you would need for feeding this. It also has to be injected in a proper mix zone. You can't feed it in low flow areas. It will not mix. You've got to have some type of turbulation, overflow weirs, agitation, but do not use water champs. The alloys used on the water champs are not compatible. Titanium is not compatible with PAA, so and you don't need that much mixing. It's very close to the density of water. It will fully be miscible. The key is you just want it in there as fast as you can at that high dosage, and that's where you're getting killed. Also, again, bottom floor, 0.35 parts per million and 1 part per million max. And also, you know, we would like 10 minutes. I've seen places now I have to do 5 to 7 minutes. You can achieve it. It's a CT variable. You're going to have to go with higher dosages. But again, you still have to achieve less than 1 part max in the discharge. So as you see, there's a lot of data here. We've done extensive testing on the product. We know that once it's applied correctly, it will work. You have to overcome some of the challenges with the waters coming in. You have to understand the chemistries of the water. You have to understand the interactions. You have to understand what the solids do, what portion has organic solids. So there's a lot of variables here when you put together that you have to evaluate before you can actually say, let's do a full-scale evaluation. With that, I think I've taken my time up. I'd like to thank everyone for this opportunity, but again, if you need references, I can forward those through Gary. You know, the folks we have dealt with are more than willing to discuss the results with you and go forward. So thank you again.
Thank you, Bob. Appreciate that so much. You've got a lot of questions, and we're not going to be able to answer all of them, at least at this point in the webinar. But I do have one question before we move on to our next speaker. Can you describe the facilities at Steubenville? What was made up there? You know, was it an existing tank? Was it made out of concrete? How was the neat solution injected into the water? Could you just share a few comments on how you approached that in Steubenville?
All right, we had to make sure we had the combined discharges from the 3 clarifiers. We're lucky there's one pipe that goes down, makes a 90-degree turn, and goes directly to the old chlorine contact chamber. It's a typical 30-minute design, concrete basin with overflow weirs. They've installed a couple of extra weirs for mixing. They have stainless on overflows, so they've put some modifications in there. But again, very simple design system. One of the limits we found at Steubenville, though, is that the pumps they had were not variable speed. So at times we may have 8 million gallons a day, and then it drops down to 3 million. I was there one afternoon and we saw 0. So those are some of the problems we had to overcome hydraulically to demonstrate how the product worked. But very simple systems. We applied it directly into the middle of that combined pipe. It was a 24-inch pipe that came down and took a 90-degree turn. We did dye tests to verify the flows that actually hit. We injected dye and tested it as soon as it hit the head wall, so we knew 5 seconds was the time frame at 7 mgd. So a very simple system, not a lot of moving parts, but again, the key is that we use the discharge flows as our controller, and we're continually meeting the 0.3 to 0.4 discharge into the Ohio.
Thank you so much, Bob. We need to kind of move on to our next speaker. Our next speaker is Alberto.
Ready to go, Gary?
Yeah, okay. Alberto Garvey. I'm sure I'm pronouncing that wrong, but Alberto goes by Alberto. That's the easy. Alberto is the Director of Business Development at the Peracetic division of FNC Corporation, where he is responsible for the company's water treatment business. He's worked in the chemical feed and disinfection of municipal water and wastewater for more than 12 years. He holds a bachelor's degree in chemical engineering, a master's degree in environmental engineering from Drexel University, and MBA degree from Rutgers University. And with that, we'll invite Alberto to share with us some of the experiences that FMC has had in terms of application of peracetic acid in the water, in the wastewater industry. Alberto?
Thank you, Gary. Thank you, Gary, and thanks to the audience for taking the time to participate in this webinar. Over the last 2 years, a number of North American wastewater plants have evaluated, in some cases, implemented PAA disinfection. The goal of this presentation is to share data from field applications that advance our understanding of this technology. Over the next 25 minutes, I'll share with you field data sources, what drove these plants to evaluate PAA, what parameters determine PAA efficacy, and what engineering factors were critical in the implementation of PAA systems. Finally, what kind of involvement have regulators had with some of these plants? This presentation is based on data collected from 18 field applications of Vigorox WWT2, which is the EPA-registered 15% PAA, 23% hydrogen peroxide solution produced by FMC for wastewater disinfection. As a quick note, the first formulation FMC introduced for wastewater, called Vigorox WWT, was a 15% PAA, 10% hydrogen peroxide mix. After some testing, we replaced it with Vigorox WWT2 to increase the peroxide content to 23%, since it had showed better disinfection performance in the field. As you can see, applications of Vigorox in wastewater have covered a wide range of waters and climates. But what drove these plants to evaluate peracetic acid in the first place? In one word, cost. There are 4 primary drivers that drove these plants to look for more cost-effective solutions. The number in the circle represents the number of plants out of the 18 that fell into each of the categories. In the first category, plants facing chlorine toxicity issues wanted to avoid the high operating cost of dechlorination. In the second category, plants with disinfection by product permits needed to replace chlorination, or wanted to avoid capital spending. In the third category, plants running with very high chlorine doses wanted to reduce chemical cost. And in the last category, plants with new disinfection permits needed to increase contact time, or chlorine dose, or UV capacity, or wanted to minimize cost. In all these cases, PAA had the potential to reduce operating costs or avoid capital costs. So let me provide more detail on each of these cases. In our first case, plants using chlorination had to comply with a new chlorine limit of 0.01 ppm. In order to meet this limit, plants like Florida 1, Ontario 1, Illinois 1 were considering addition of a dechlorination step by feeding sodium bisulfite before discharge. The additional cost of dechlorination drove the cities to evaluate alternatives like UV disinfection and Vigorox PAA. While the operating cost of the 3 alternatives was basically the same, these plants preferred Vigorox because of its simplicity. PAA does not require quenching, so it can be implemented as a one-chemical solution. On the capital cost side, Vigorox was also preferred, since tanks and chem feed equipment are leased to the cities at a nominal cost. Now, some states have established maximum limits for disinfection by products in effluents discharging to public waters. For example, in California, many plants have limits on THMs as low as 60 parts per billion. Some plants in Florida have a cyanide limit of 1 part per billion. We know that both THMs and cyanides are formed when chlorine reacts with organics in the water during the disinfection process. So in these cases, the only viable option was to replace chlorination with some other means of disinfection. Here again, plants compared UV disinfection against Vigorox peracetic acid, and once again, plants were able to avoid significant capital expenses by converting to PAA disinfection. The high chlorine demand case is typical of plants that treat a significant amount of industrial effluent or plants that produce primary effluents. In these cases, chlorine doses are high, typically around 30 to 40 ppm, representing very high chemical costs. Replacing chlorine with UV in these plants would not be practical or cost-effective, since the low transmittance of the effluent would require too large of a UV system. On the other hand, with Vigorox, plants observed lower operating costs and avoided capital expense, since again, the equipment is leased at a nominal value. Finally, a number of plants were interested in evaluating Vigorox because they were facing permit changes that would require an increase of disinfection capacity. A plant in Tennessee has recently been required to disinfect for the first time. High variations in effluent quality made UV too expensive for this site. And since Vigorox required a smaller contact tank than that needed for chlorination, it became the most effective solution for this site. A plant in Texas used the outflow pipe to provide chlorine contact time. When the effluent quality worsened and the flow rate increased, the plant had to consider a new contact chamber and the addition of dechlorination step. Here again, the evaluation of Vigorox showed that the plant could save both capital and operating costs by switching to PAA. So we've established that PAA can be cost-effective in the cases we just described. But what determines whether PAA can be cost-effective at any given individual site? In other words, how do we know how much PAA and how long of a contact time is required to meet permit limits? Well, we know that the effective dose of PAA is primarily driven by three factors. First, the indicator organism listed on the permit. Some permits use E. coli, others fecal coliforms, others enterococci, and not all permits use the same limit. Some use 200 CFU per 100 ml, some use 23, etc. The second factor is the demand for PAA created by all constituents in the water. Before disinfection can occur, enough PAA needs to be added to satisfy the demand. In most water applications, demand is proportional to total suspended solids, total organic carbon, and biological oxygen demand. And contrary to chlorine, ammonia does not create demand for PAA, which can be a significant advantage. Finally, the contact time available has an impact on the required dose. In general, higher doses are required to achieve disinfection in shorter contact times. So let's review these three factors in more detail. Regarding impact of indicator organisms, let me start with the published literature. The effectiveness of PAA against bacteria in secondary wastewaters has been well documented. Most of these papers conclude that doses ranging from 1 to 4 ppm and contact times of 10 to 20 minutes would yield 2 to 4 log reduction in bacterial organisms. A simple way to visualize all this information is to plot the product of PAA concentration and contact time versus the log reduction achieved. Plotting all the published data would yield a graph like this. On the x-axis, we have the product of concentration times time. On the y-axis, we have the resulting log reduction. The blue diamonds represent all the data published for PAA against bacteria in secondary wastewater. The blue shaded area covers the effective range of PAA against bacteria. Virus reduction in wastewater is typically not a concern and not part of NPDES permits in North America. So the literature here is very limited. There is some published data on PAA in wastewater for reduction of MS2, a common surrogate for viruses. These data points are represented with the green circles. And there is not a lot of literature on PAA biocidal efficacy in wastewater. The data shown here as green triangles shows PAA efficacy against viruses in the mineralized water. Clearly, reduction of viruses is far more intensive than reduction of bacteria. So now that we have established these operating regions, it would be interesting to see where the data points coming from the 18 Vigorox applications fall. Let's start with the biocidal data coming from Ontario 1, shown here as black squares. FMC partnered with a city in Ontario to conduct a third-party study on the efficacy of PAA against viruses in concentrations ranging from 1.5 to 4.5 ppm. As you can see, at low CT values, the results were consistent with published MS2 data in wastewater. And at high CT values, the results seem to align well with the area that joins the two green regions. More importantly, this study demonstrated that PAA can achieve virus reduction levels equivalent to those of chlorine in wastewater. Let's now look at the Vigorox bactericidal data shown here as black circles. As you can see, the Vigorox data points are also fairly consistent with the literature data. But one important thing to note is the wide range of CT values that could deliver a given log reduction. Take, for example, MO1 over here, that's a plant in Missouri, and CA1 over here, a plant in California. Both plants achieved a 3 log reduction, but in Missouri, a CT value of 24 was required, down here, versus in California, where the CT value was 360, down here. This significant difference in CT values is due mostly to the demand that all constituents in the water create for PAA. So it is critical to understand what causes demand and how demand behaves. For example, this secondary effluent from a plant in Minnesota was treated at different vigorous concentrations and different contact times. A dose of 1.75 ppm did nothing, regardless of contact time. We gradually increased the dose with almost no disinfection results until we reached 6 ppm and finally got a 3 log reduction of E. coli. In order for disinfection to occur, we first needed to satisfy the PAA demand with a dose of 6 ppm. So the question is, what determines that initial demand? We know that certain water quality parameters such as total suspended solids, total organic carbon, and biological oxygen demand increase the demand for oxidants in general. They increase demand for PAA just as they increase demand for chlorine. We also know that the demand is not an absolute value. In many cases, it is a function of dose. For example, at this Tennessee plant, we measured the drop in PAA concentration over time. As expected from demand kinetics, PAA demand increases from 2 to 5 ppm, which would be the drop from the first point to the second point, or the first point to the second point here, as the initial PAA concentration increases from 4 to 10 ppm. understanding demand behavior is critical for process control, since those parameters that increase demand may change over time. An additional challenge is that in many cases, demand does not correlate well with any of these parameters. For example, another plant in Tennessee receives industrial effluent several times per month. Every time this happens, color increases significantly, but TSS or VOD remain fairly constant. A Vigorox pilot was conducted at this plant and demonstrated a strong correlation between color and PAA demand. There was no correlation with TSS. The same phenomenon was observed in other high-demand sites like Washington 1 and Minnesota 1. The bottom line here is that demand may have different sources in different plants. So let's review now how contact time impacts PAA disinfection. Many studies have shown that PAA can achieve the same disinfection performance than chlorine at shorter contact times. This can be critical for plants that have to spend on new contact channels. This was the case for a plant in Texas. In order to meet permit limit, they needed to build a new contact chamber. Obviously, if they could reduce the contact time required without increasing the dose too much, they could save a significant amount of money. A pilot test of this plant demonstrated that contact time could be cut in half with Vigorox at similar operating costs than that of chlorination and dechlorination. A pilot study conducted in Washington State showed that the bulk of disinfection was occurring in the first 5 minutes of contact time. In parallel, we developed a computational fluid dynamic model of the pilot reactor to be able to simulate conditions that cannot be seen easily at the plant. For example, an increase in the influent coliform count from 10,000 to 100,000. The use of the CFD tool shows that in general, the bulk of the disinfection should occur in the first 5 to 10 minutes of contact time. Once more, data from field applications advanced our understanding of PAA disinfection. In fact, the next case will illustrate how PAA can interact with other disinfection methods. The study was conducted at a plant in New York State where Vigorox was fed upstream an existing UV system. The UV system that normally operates at 40 millijoules per square centimeter was set to run at 50% of lamp output with a dose of 1 ppm Vigorox. The results showed the same fecal coliform log reduction for both UV alone at 100% output and UV at 50% output plus 1 ppm of Vigorox. While more research is needed to define operating parameters under which cost is minimized, this study suggests that a 50% reduction in power consumption is possible and could be very significant for large UV plants across the country. So let's change gears now and discuss the engineering aspects of implementation of Vigorox disinfection systems. Let me start with storage considerations. When bulk storage tanks are required, we must consider containment, chemical compatibility of all materials, average temperature versus PAA shelf life, and appropriate venting. Typically, FMC would lease 6,000-gallon double-walled linear polyethylene tanks equipped with all safety features and replace them every 5 years at no additional cost. Please note that in addition to temperature, the rate of loss of PAA in storage is a function of two things: the purity of the raw materials used by the manufacturer and the process by which PAA was produced. It is important to understand this because two PAA solutions of the exact same formulation may have very different shelf lives. Very similar considerations apply when using 300-gallon totes. In general, containment, materials, and venting need to be considered. Typically, FMC would lease the tote containment units and related piping. On the pump side, PAA can be fed with peristaltic, diaphragm, or solenoid pumps. There is some off-gassing with PAA, but for the most part, it can be handled with off-gassing valves, just like the ones used in sodium hypochlorite solutions. And again, containment, materials, and venting need to be considered. On the piping side, it's a good idea to always use flex connections for totes and tanks. A standpipe can be used for venting the line connecting tanks and pumps. And it is also a good idea to set up a water connection to flush the line prior to maintenance work. On the control side, we moved from flow-through cells to the latest generation of submersible probes to eliminate line fouling issues. We conducted extensive testing of candidate probes at our lab and are in the process of obtaining a third-party validation of the accuracy and reliability of this latest probe for Vigorox residual measurement. Having the ability to measure PAA residual online is critical for consistent implementation of the technology, since it allows monitoring for reporting purposes and feed rate control based on compound loop schemes. This winter, we had the opportunity to run a full-scale demonstration at a plant in Illinois during the infamous polar vortex. Temperatures plummeted to -30 degrees, but the Vigorox system continued to operate flawlessly. The key here was the low freezing point of PAA. As you can imagine, this property allows plants to save in insulation and heat tracing compared to chlorination and dechlorination systems. One of the most important things that we have learned over the last 2 years is that the key to a smooth conversion to PAA is the early and frequent involvement of your state regulator, especially when it comes to definition of testing and data analysis protocols. From Ontario to Florida to California, early regulatory involvement have allowed plants to run the right trials, generate the right data, and present it in the right way. I cannot overestimate the importance of involving your regulator early in the process, and I invite you to do so as you consider potential evaluation of this technology. I hope to have shown you convincing data on the potential of this technology to enable disinfection compliance at competitive operating costs while avoiding additional capital expenses. We are very proud of the work we're doing and of the advances in PAA wastewater disinfection we have achieved with Vigorox WWT2. Before I conclude, I would like to acknowledge the help and collaboration we've received from multiple organizations in the industry. Drexel University on developing our CFD disinfection model, the Politecnico di Milano on providing fundamental kinetics data for PAA modeling, the Rochester Institute of Technology on conducting the UV Synergies study, HDR Hydroqual on performing the third-party validation of instrumentation, CDM Smith on designing our pilot reactor, Carollo Engineers on producing the literature review on PAA disinfection, AECOM on defining testing protocols for virus efficacy in Ontario, and finally, Montgomery Watson on developing modeling tools to assess fate and impact of PAA residuals post-outflow. I want to thank you all for your time and hope this presentation was time well spent for you. Thank you.
Thank you so much, Alberto. You've received as well a number of questions, and we can probably answer one before we go on to our next speaker. If you could, out of curiosity, if you know how many states have, in the United States at least at this point, have approved PAA as an alternative disinfection approach?
Well, I would say that there's a number of states that are allowing the evaluation of PAA, but ultimately each plant needs to get a permit modification to be able to use the technology. So we haven't seen a statewide blanket approval to switch. So rather, plants are encouraged to run pilots and full-scale trials, generate data, present that data to regulators, and then apply for a permit modification.
Thank you so much, Alberto. We'll now move on to our final speaker in this webinar. Our final speaker is Glebra Skip. Glebra was born, raised, and now is currently working in St. Augustine, Florida. She graduated from Stetson University with a bachelor's in biology, and she prepared a presentation recently on the application and implementation of PAA at her wastewater treatment reclaim facility in St. Augustine, Florida. Glebra enjoys photography, gardening, and kayaking, and a number of the pictures on the presentation that you'll see of the treatment plant Glebra actually took. So we're actually excited. She does a very good job. And with that, Glebra, if you could address the group here.
Thank you, Gary. I'm, like Gary said, with the City of St. Augustine, and my presentation is on our experiences with peracetic acid disinfection. We've been using peracetic acid as our primary disinfectant since December 2011. So for over 2 years, we've been using peracetic acid. A little background on us. We are located in St. Augustine, Florida, which is in the northeast part of the state between Jacksonville and Daytona. Our wastewater treatment plant is permitted for 4.95 million gallons per day. And last year, our annual average flow was 3.88 million gallons. Our process is complete mix activated sludge. We discharge to surface water, and we have on-site only reuse. We don't distribute any to our customers. The city was approached by an associate of FMC Corporation to conduct a pilot study comparing chlorine and PAA disinfection. Our wastewater plant has 2 identical contact chambers, making it ideal for a side-by-side comparison. So at the time, we decided we were interested in saving money over chlorination and dechlorination, and also preventing the formulation of disinfection byproducts in anticipation of future stricter regulations. This slide gives an overview of the timeline in which we implemented our pilot study and our full plant disinfection. We are regulated by the Florida Department of Environmental Protection, which you'll hear me call DEP. So our pilot study was in April through June 2010. And then in July 2011, the city submitted its permit modification to DEP for full plant PAA disinfection. And then in September 2011, DEP issued our permit modification, and we depleted our current chlorine supply, and then in December 2011, we began our full plant disinfection with PAA. We had to submit a 6-month operational report, and based off of that report, we did submit for a few minor permit modification requests. And in August 2012, DEP did issue a permit modification granting those requests. So we've been using that permit for our peracetic acid since August 2012. Our pilot study was conducted from April through June 2010, and this diagram shows how we set up our trial study. So you can see that we had one contact basin disinfecting with 12% sodium hypochlorite and the other with 15% Vigrox peracetic acid. After the contact basins, the water combines into a common tank where we pump our reused water from, and then it enters into the post-aeration basins. We did dechlorinate with sodium bisulfite just before our final effluent as part of our operational permit for the chlorine disinfection. We based our continued use of peracetic acid on disinfection performance, aquatic toxicity results, disinfection byproduct results, and chemical consumption and cost. I'm not going to go into the details and the results of our trial study in this presentation, but if you are interested in seeing our actual sample data, we did write a paper comparing the 2 disinfections for WEFTEC 2012. But you can see that our fecal coliform results were almost equivalent from peracetic acid to the chlorine, and also our disinfection byproducts were were much, much less with the peracetic acid. They were non-detect versus the chlorination and dechlorination, which were actually above some of the surface water limits. I did want to show the difference in the color of the wastewater because we get asked this a lot. With chlorine, you see you get that bleached swimming pool look, but with peracetic acid, our wastewater is definitely darker, and to us it reminds us of some of the tannic North Florida river water. We had to make very few, very minor facility modifications for the conversion to full plant peracetic acid. We worked very closely with FMC to set up our system, and the first thing we had to do was install 2 Peracetic pumps that would allow us to pump the PAA to our injection location. You'll see the picture. We used 2 Flow Motion Series 2001 HEC Peracetic pumps with tube rupture detection, and these pumps were configured into our SCADA system and set to dose the PAA proportional to our flow. We had 2 containment assemblies installed to hold the PAA totes for feed to the pumps. The Peracetic pumps you saw in the last slide are housed just on the other side of the concrete wall here in this picture. We converted our existing chemical storage facility into our PAA storage area by simply adding a concrete spill containment curb. The PAA is shipped to us in one-way totes from New York. When we receive a shipment, we use a forklift to remove the totes from the semi into our storage area. With our new discharge permit, we were required to maintain the chlorination-dechlorination system as a backup. This includes our chlorine feed system and chlorine storage tank. Our new limits were a minimum PAA dosage of 1.5 parts per million and a maximum effluent residual of 1.0 part per million. We were required to monitor the effluent residual continuously, so we had an analyzer installed at our final effluent, which was also connected to our plant SCADA system. We also needed to collect a daily effluent grab sample, which we analyzed for residual with our single analyte meter. We knew that PAA would work as a disinfectant, but because we were retrofitting it into our existing system, we were prepared to tackle any operational challenges that might arise. It came down to our ability to troubleshoot and sometimes think outside the box. Most of our operational challenges were plant-specific, so there's a good chance that someone else starting up a PAA system will never have to encounter what we did. We didn't really have a neighboring wastewater plant to call up and ask if they've ever experienced what we were experiencing. So hopefully some of the lessons we learned along the way will help others and enable them to quickly solve their challenges, or maybe even prevent them from happening to begin with. One good thing is that working through these challenges has ultimately given us a better understanding of our plant. So our first operational challenge was our dosing location. We initially had the dosing location set up to inject the peracetic acid at the end of our clarifiers. We chose this point for 3 reasons. We wanted to increase our retention time, allow for greater mixing, and reduce the volume of chemical required for disinfection. So you can imagine how baffled we were to see fecal coliform plates with background colonies on them. This was something we had not seen at all during our trial study. So we started collecting a lot of samples at various locations, trying to figure out what the issue was. I tried with this image to find one that would actually show what we were finding. The background colonies are the ones that are light brown, and the fecal colonies are the ones that are blue. You can see we had a lot of background colonies. So we found that by the time the water was arriving at the contact basin, a lot of the peracetic acid had already been consumed. We checked the pumps, and there was no problem there. So that led us to the pipe that conveys the water from the clarifiers to the contact basin. Looking at plans and elevations, we were able to discover that this pipe, which is the red pipe on the diagram, is actually reverse slope, and solids were accumulating at the low end of the pipe. This was placing a really high demand on the peracetic acid and consuming a lot of the disinfectant before it reached the contact basin. So relocating our dosing point approximately 500 feet downstream solved the problem of the background colonies. Point B on the diagram is our relocated dosing point. It's close to where we were in our trial studies, and it still gives us sufficient mixing prior to the contact basins. Our next operational challenge was extending contact time. As mentioned previously, our plant has 2 post-aeration basins after the contact basins. Our trial study could only compare the disinfectants up to the end of the contact basins before the water combined and entered into the post-aeration basins. When we went to full plant PAA, the addition of the post-aeration basins tripled the recommended contact time. So we're having to increase our dosage to 3 to 4.5 parts per million to maintain a residual, which was double what we had used during our trial study. So in our 6-month operational report to DEP, we recommended relocating the compliance point for fecal coliform and entero to the common tank. We met with DEP on site and showed them the situation. It isn't very usual to have the post-aeration basin after the contact basins, so they were completely okay with it, and we submitted a minor permit modification. And in August 2012, our sample collection location was revised to reflect the common tank. Another challenge for us was the growth of algae in our basins. It was in both our contact basins and post-aeration basins, but primarily in the post-aeration basins where the PAA was lower, residual. Our sluice gates that allow us to isolate the flow and clean the basins were leaking so badly that we weren't able to clean out the algae as much as we needed to. And when algae was present, we had to increase our PAA dosage to maintain a residual. So we did get the new sluice gates installed last July, and we've now implemented a quarterly basin cleaning schedule. And now we're going one step further, and we're actually coating the interior of these basins. That's going on right now as we speak. We probably won't know for sure that we've solved the problem until the heat of next summer, but we're confident that we have a lot better control of the basin algae. Another operational challenge was continuously monitoring our effluent residual. So the requirement of our permit to continuously monitor our effluent residual was a challenge. As I mentioned before, we did have an analyzer installed at the effluent. The problem was that the PAA was already depleted by the time it reached the analyzer, and algae growth in the analyzer and in the tubing required constant staff cleaning, typically 2 to 3 times a day. And even cleaning that much, we were unable to keep the growth from reappearing. Our solution was to present DEP with data that showed that our residual is never even close to our 1.0 limit. Typically, we're at a 0.1, mainly because of our post-aeration basins. So even when we dosed 4.5 parts per million for 21 days, our highest effluent reading was a 0.5 part per million. We also have 1,600 feet of outfall pipe that allows the PAA to further deplete before discharging to surface water. So as part of our 6-month operational report, we recommended removing the continuous effluent monitoring requirement, but continue with the daily grab samples. Having a continuous meter is not a bad idea, though, and we did try a second version at the common tank. And this would allow us to actually see a PAA residual in the system before seeing a low at the effluent. However, the second model was better than the first, but we still ran into a lot of algae and problems keeping it clean. So we're currently waiting the newest version, and we're hoping that that's going to be the winning model for us. As far as maintaining a residual, all we do is set our dosage and we're done. We don't need to make many adjustments at all unless our demand changes, which typically would only be if our basins are nearing time to be cleaned. When we check our effluent residual, if we do get a low reading, we check our common tank residual to make sure that there's no issues with the system. And like I mentioned, when we get the new version of the analyzer, we're hoping to have it at this location, so it'll help us with the monitoring. The monthly maintenance only takes really a few minutes. We change the Peracetic pump tubing, we put dry silicone spray on the pump rollers, and then clean out the filter baskets. This graph shows our cost effectiveness. We did our initial cost study at the beginning of 2012 using the cost of the sodium hypochlorite and sodium bisulfite from 2009 versus our cost of PAA in 2011. We determined that our break-even point would be around 2.5 parts per million PAA. And as you can see, it really fluctuated a lot, but it wasn't until we got all of our operational challenges worked out that we finally have been consistently under that break-even point. We're currently dosing 1.9 parts per million, which is equivalent to 11 gallons of PAA solution per million gallons of flow. We have not used chlorine since December 2011. Our average PAA dose in 2013 was 2.6 parts per million with a trend downward. Our sluice gate install was a big hurdle, and since that installation, we're down to an average of 2.0 parts per million. Our average effluent PAA residual in 2013 was a 0.06 parts per million, which is significantly less than our 1.0 permit limit. And you can see I put a graph in here of our fecal coliform averages for 2013. Our permit limit annual average is a 200, so we are well below our permit limit. So looking forward, we're working with FMC to convert from totes to a bulk tank. This will eliminate a lot of our handling time, which increases the odds of having an accident happen. We haven't had anything happen to date, but it will be nice to go to the bulk system. We're also working to have a flow meter installed on the peracetic acid line just after the Peracetic pumps. And this will allow us to calculate our dosing coefficient from an actual meter instead of using the pump hertz, which is what we're doing now. And that's it. Gary, back to you.
Thank you, Gabriel. You've got a number of questions here, and we have a few minutes here before we move on to our next topic. Could you share a little bit more in detail about the process that the treatment facility went through in approaching FDEP and the regulators, and that process, and what concerns, questions, issues that FDEP require to be addressed before you could get your final operating permit?
Yes, well, and actually FMC worked a lot with us on that. They helped us get the initial pilot study going, and then we kind of, after we got our official permit, we kind of took over from there, doing a lot of the communication with DEP. But FMC really helped us out on that. And they wanted to see, we did the bench testing in the lab. We presented results on that. But that was really our extent of the beginning.
Oh, thank you. That was really good. One of the folks wanted to know what you see as your tube life on your parasitic pumps with the use of the peracetic acid.
We're changing out the peracetic pump tubing once a month, and that's the recommended time on that. So we are following the recommendations for that.
Another question was asked. You said you were coating your basins. Do you know the name of the coating that's being used, by chance?
It's a Sherwin-Williams coating. I'm not sure exactly the name of it, but it's going on right now. So I'm not 100% on the exact name, but it's a Sherwin-Williams coating.
Okay. Well, thank you.
I can get that. If someone wants that directly, I can provide that to them.
Okay. Thank you so much, Labra. I think we'll move on to our sponsor to share with us a few minutes. We do have a sponsor for this particular webinar. We're really thrilled that FMC is sponsoring this particular webinar. And so as part of the sponsorship, we're asked for a few words from our sponsor, and they have a little presentation for us. So with that, I believe it's Alberto, is it Peter that's going to take care of that?
Philip, yeah.
Philip, okay, Philip, if you could start, please.
Great. Thank you, Gary, and good afternoon to everybody. My name is Philip Locke, and I am the Technology Manager for our water treatment business. I have been with FMC for 13 years, developing new products and technologies for contaminated water, soil, and air treatment. I'm going to outline FMC's involvement with the development of peracetic acid for microbial control over the past several decades, and how we're advancing the science of peracetic acid for wastewater disinfection for the future. We've been involved in the control of microorganisms using peracetic acid for over 30 years. Since the mid-1980s, we have been selling peracetic acid to companies like Steris and Advanced Sterilization Products for the control of bacteria, viruses, and spores on medical devices such as endoscopes. Peracetic acid is capable of achieving high-level disinfection and sterilization and can kill gram-positive and gram-negative bacteria, viruses, yeast, fungi, and spores. Typical PAA concentration time dosages, known as CT values, of up to 20,000 milligram minutes per liter may be required for sterilization, depending upon the target microorganism to be controlled. In 1993, FMC launched the Vigorox LS&D trade name for the sanitization of hard, non-porous surfaces and reverse osmosis membranes. Such surfaces can be sanitized against microorganisms such as Listeria, Staph aureus, E. coli, Salmonella, Pseudomonas, influenzas, and various animal viruses. Typical CT values for hard surface applications range from about 80 to 150. 8 years later, due to an outbreak of Xanthromonas campestris on fruit-bearing trees, we launched the Vigorox Citrus XA product, which can be sprayed within an orchard to control this pest. Typical CT values for this application also fall within the range of about 80 to 150. 2 years later, FMC helped pioneer the use of peracetic acid for direct food contact with our Spectrum branded product. Applications include peracetic acid use on red meat, fruits and vegetables, and for the treatment of poultry during processing. Spectrum peracetic acid is designed to control Salmonella, Listeria, E. coli 0157H7, and Campylobacter. With an increase in food product recalls due to E. coli and Salmonella contamination over the recent years, products such as Spectrum are critical to maintaining a healthy food supply. Typical CT values for direct food contact range from 100 to about 230. One of our most recent product advancements is Vigorox O&G, which was launched in 2010. This is a product designed to prevent well fouling by controlling organisms such as sulfate-reducing bacteria, which can cause iron precipitation, and also biofilms, both of which can prevent gas production within the well. Today, we are pleased to launch Vigorox WWT2 for the disinfection of municipal wastewaters, designed to control microorganisms such as E. coli and total coliform. Our efforts in treating wastewater date back to 2007, when FMC helped pioneer the use of peracetic acid as a wastewater disinfectant within the United States, with a demonstration project in Saltillo, Mississippi, performed in conjunction with the Mississippi State University. To keep pace with advancements in peracetic acid technology and applications, our microbiology control laboratory has expanded as well. Its capabilities, including the assessment of microbial populations and log kill performance, measurement of oxidant demand and decay kinetics, and analysis of water quality parameters. During the past year, we have also added viral kill assessment capabilities with the inclusion of techniques to enumerate MS2 bacteriophage, a surrogate model for human pathogenic viruses. The science of peracetic acid is advancing. Next generation technology will take in-house and on-site PAA assessment into the realm of computer modeling, which ultimately will be tailored to simulate the peracetic acid hydraulics and kinetics for your specific wastewater treatment plant. In addition, post-outfall peracetic acid decomposition and dispersion will be modeled to provide a site-specific estimation of the impact of peracetic acid upon the local environment. Peracetic acid innovation for wastewater is here today, bringing state-of-the-art disinfection to the water treatment plant tomorrow and into the future. As we move to the future, FMC peroxygens will be transforming into PeroxyChem as a standalone manufacturing and technology company that combines the impact of a large $330 million company with the resources and flexibility of a nimble technology company. We are fundamental in peroxygen chemistry, with 6 worldwide manufacturing facilities across 3 product lines, including peracetic acid, hydrogen peroxide, and persulfate. With decades of experience, advanced laboratory capabilities, seasoned professionals, and innovative scientists, PeroxyChem can help you meet your disinfection needs. We invite you to challenge us with your problems. And thank you very much for your time, and we hope you enjoyed the presentations today.
Thanks so much, Philip. We'll now move into our question and answer part of the webinar, which I'll lead and then pose questions to each of our different speakers. I'll just note that the webinar ends at the hour, so we'll be finishing at that point in time. Just to note, one of the questions asked about future presentations / webinars on PAA. Currently, there is planned for a full session at WEFTEC 2014 in New Orleans on peracetic acid. The Disinfection and Public Health Committee at WEF views this as a very hot topic and one that people are very interested in, and so a session has been fully dedicated to PAA as well. There will be a second webinar on PAA. It probably later part of this year, early part of next year, on visiting more about the application and implementation of PAA. So with that, we'll ask our first question. This will go to Glabra, and one of the attendees asked if you could address safety issues with the PAA and anything that you'd like to discuss relative to safety, from a chemical handling standpoint and other issues associated with it.
Sure. If any kind of peracetic acid, if there is a spill, the solution is dilution. So we do have water taps available that if there was a spill, we could easily turn on water to dissipate that. We do have eye washes that are located near our containment, tote containment facility. And also we do have some other, we have, I'm sorry, I'm getting tongue-tied here. We have some masks and whatnot if our operators do use them. We haven't had any safety problems using the peracetic acid, but as I did mention in the presentation, we do want to go to the bulk system, which will nearly eliminate any kind of potential exposure that we would have with the peracetic acid.
Thank you, Glabra. This is for each of our panelists or speakers today. And I'll start with Glabra, since you're the one that's probably been the most. But there have been a number of questions that have come up relative to the analytical methods associated with peracetic acid and the detection limits and the accuracy of those methods. Can you address that? Then we'll ask Alberto and Bob to address that as well.
Is that referring to as far as the analyzers and
the grab sampling methods as well as the analyzers?
Okay. Well, for the grab sampling, all we do is we take a sample, and we do have a single analyte meter that is colorimetric, and we do run a test on that where we do a titration, and we check that the meter is actually performing accurately based off of our titration, and it does seem to be very accurate for what we're using it for. I can have a titration of a 1.0 part per million, and I have hit a 1.0 on the single analyte meter. So I believe it is fairly accurate. I think the analyzer is also, in theory, more accurate than the single analyte meter, but we weren't able to experience that very much because of all the algae that we had in the analyzer. So once we get the analyzer without algae, I do believe that will be very, very accurate.
Hey, Alberto, any additional information relative to analytical method, sure, repeatability for PAA?
Sure, no problem. So, just like we do have for chlorine, there are colorimetric methods and amperometric methods. The handheld device that Glabra was referring to is based on a colorimetric method. And the online analyzers, again, just very much like the case of chlorine, is an amperometric device. I believe that the method itself is very reliable, and we've been collecting third-party data to be comfortable with it. I think that one of the challenges that we experienced in the past was, as Glaber mentioned as well, to maintain the lines in a flow-through cell clean. That problem goes away if you don't have any lines and you have a submersible probe, which is the way we're going.
Bob, can you add any more to the analytical methods for PA?
Sure. The test method that you use is the same as total chlorine. It's a DPD method. You get the tint coloration. The colorimeters will give you the concentration. That can be measured down to 0.1, 0.05 parts per million. So you can handheld down to a very low level. The problem with amperometric is that the sensitivity up to at least a year ago was only about half a part per million. So we're controlling down to the 0.3 range. We had a problem online with the amperometric. They modified the cells, some of the suppliers, so they believe they can get down. That's what we're running through at Steubenville right now with an online monitor, and that's what we use for control. But the same method. Now the key is when you do the DPD is that you have to take the test within 15 seconds. The peroxide in the product will activate the DPD, so you'll get a false reading if you go beyond 15 seconds. This is key to people that are doing analytical work in the labs when they're following typical test procedures. You have to do it quick. You'll get an instantaneous PA level. You multiply the result on the chlorine analyzer times 1.07, and that's your PA residual. So again, you have to be careful of how it's done. You cannot use the typical total chlorine methods.
Thank you so much. Glebra, this question's for you, and I know you addressed it, but if you could just reiterate the current and design flows for the St. Augustine plant.
Okay. As far as our basins, our flow, our average daily flow coming in, we're permitted for 5 million gallons, or 4.95, and our average last year was 3.88. Our contact basins, the flow time, I did have that on one of the slides so that you could go back and look at that. Our peak is around 20 minutes, and I'm pulling that up right now for you. Our peak detention time in the contact basin is 23 minutes, and our average flow detention time is 47 minutes there. In the post-aeration basins, we were adding another 36 minutes for peak flow and then a 47 for our average flow. So that's where we ran into the problems with that post-aeration basin, extending our contact time a little too much for what we needed, and we were having to increase our dosage.
Thank you so much. This question is for Alberto, and then we'll pose the same question to Bob. One of the attendees asked, where in the U.S. currently is, or locations is PAA currently being produced? Alberto?
Yes, thanks, Gary. So right now we have production facilities in Buffalo, New York, and we have the ability to produce also in the Midwest. And as we develop the market a little bit, we'll have the opportunity to set up production facilities in freight logical locations across the country.
Okay. Bob?
Well, we represent Solvay. So Peregrine is working directly with the Solvay Chemicals Group out of Houston. They're the world's largest producer in the world. So they basically have distribution centers, production hubs throughout the U.S. We've looked in California, Florida, East Coast, West Coast, and again, they can store the product. Right now, it's produced in Joliet, Illinois. We've talked about other production facilities with toll blenders. We've talked with Solvay about producing the product itself at these storage or distribution hubs. So right now, again, based on the market size, we're looking at the geographical areas that have shown interest, and we're gunning up to make sure we can produce in those areas. But right now, the capacity is anywhere between 5,000 and 6,000 gallons a day for distribution out of Illinois.
Thank you. The other question that has come up, this is for Bob and Alberto, is largest facility size that currently that you folks are supplying for PAA?
Maximum 13 million gallon per day, nominal 7 to 8, with bypass up to 30. 35, I'm sorry, 35 million gallons per day. So that's the size of the largest facility that we're treating at this point as a waste treatment plant.
Alberto?
Yeah, on our side, currently it would be 5 to 8 million gallons a day. Hopefully, in the near future, that number would go to 40 MGD.
Thank you so much. This is probably for Bob and or Alberto. If you could offer some comments relative to the cost of PAA versus the cost of chlorine, and where do you see the point of inflection for those two chemicals?
All right. The study we did in Steubenville, again, went from PAA back to bleach and back to PAA. During the bleach study, the customer wanted to run his own demonstration to make sure that he applied the same product to the same dosage, did the evaluation himself, and basically demonstrated the fact that he saved 25% or greater than the cost of chlorine and bisulfite. So that's the one demonstration we have. I see this continual throughout the East Coast. The West Coast has very low costs for chlorine bleach, and some places don't have to dechlorinate. So that'll be a concern with trying to match pricing. But if you take a look at chlorine dechlor, you can be lower if you're applying the product correctly. If chlorine is being applied correctly and you're applying the bisulfite correctly, you will see a reduction.
Alberto?
Yeah, I agree with that statement. In general, I think it's fair to say that the cost of PA disinfection is lower than the cost of chlorination, dechlorination. But as mentioned, during the presentation, there are a number of site-specific parameters that will swing that evaluation one way or the other. So at this point, it's almost like a site-by-site evaluation to understand where the economics are. But as Bob said, going or comparing against chlorination, dechlorination, you typically have an advantage. The other thing to consider, of course, is the capital cost side. When compared to UV disinfection systems, obviously the capital cost is significantly lower. And in the case of FMC, where the equipment is provided under a lease, that cost is eliminated.
Well, we have a question that talks about do you know if there are studies that show that PA affects living organisms in receiving waters? I'll pose that one to Alberto first, and then we'll pass that on to Bob. In terms of toxicity or toxicological effects of PAA on receiving streams.
Right. So the toxicity question is a frequent concern for regulators. Normally, the requirement is to run a wet test where you expose a given species that typically is a species native of the stream that is receiving the treated effluent, and you have to demonstrate that if that organism is exposed to PAA at a given concentration for a given period of time, you can assess what percentage of organisms would survive that. So that's the typical wet test that has to be done. The species that you use as indicator organism changes from state to state. So, again, this is one of the areas where you want to involve your regulator early on. There is a number of data that has been published both in Europe and in the U.S. in terms of toxicity against a number of different species. In some states, regulators have been okay with published data. In some other cases, regulators want a toxicity test conducted for that particular plant for a given species that is native to the receiving stream. So one last thing, there is also the possibility of doing computer modeling on the fate and impact of a residual on the effluent once it hits the receiving water. That's the core mix simulation that is out there, and in our case, we're running with Montgomery Watson.
Bob, would you like to address that?
Some actual data that we have. The work we did in Steubenville, one of the cases that Ohio required was that we meet the current wet test conditions. We ran at 0.45 parts per million discharge, passed 100% acute wet testing. We wanted to go higher. We wanted to go up to 1 part per million. Never had the opportunity to do that summer. We had a lot of rain conditions. But that's our plan, is to get up to the 1 part per million level, redo the wet test to see what the actual on-site evaluation is. Now, one point I'd like to make again, which I brought up in the presentation, is that the work we've done after discharge is key. Because when we find there's a background in the river, that's key when you take a measurement of the flume and demonstrate the fact that it's gone or exactly the same as what you're seeing out in the river. Now, that causes a little problem now with the regulators, to where, how do we regulate it? What limits do you put on it? What's the residual life? The tests we've seen in 15 seconds, it's gone. It's not there, or less. I mean, we've done 20, 40, 60% concentrations and don't see the residual after 15 seconds. So now, where do you test? So it's kind of changing the rules the way chlorine used to be tested, because you would see that. You would see it dissipate on a plume. You could do it. You can model it out into the plume. But the work we've done on a discharge stream so far in the last summer, I had an intern working with me doing all that work last summer, and it was amazing how fast the product was gone where we couldn't detect it. So, the challenge now is, how do you rewrite the limits? But Ohio, I want to also make a point that Ohio is approving the product for use throughout the state. We've demonstrated enough. The data we gave them, all the test data, all the results, were being called by other locations all the way through Ohio, from Toledo down to Portsmouth. So the word is getting out through the local offices with the Ohio EPA. So it is being condoned by the state at this point.
Okay. Thanks, Bob and Alberto, for answering that particular question. I'll just mention that the questions have been continuing to come in. There are approximately 150 questions, so we're trying to address them as we can and highlight those questions that are not answered or are not addressed as part of the webinar. Each of the speakers will get a list of the questions, and we'll get their responses, and then those who have participated in the webinar hopefully within the next couple of weeks, we'll send out a separate answer to all the questions that are being discussed within this webinar. So question doesn't get answered, it will get answered by our panelists here today in terms of responding back to that question. One of the questions that did come up, and this is more for Alberto and Bob as well, is there any work currently being done looking at the application of PAA in reclaimed water applications? We'll start with Bob.
In reclaimed water, well, if I can you make a statement here. This is what I usually use. The good part about PAA is it's non-persistent. The bad part, it's non-persistent. Good part about chlorine, it's persistent. Bad part, it's non-persistent. Now, you can read that two different ways, but basically, if you try and put it in a reclaim or a storage water container, it will dissipate over time naturally. So if you hold the water for a long period of time, you could have regrowth. That's opposed to chlorine, which maintains its residual over a long period of time. So, that's why one of the problems with drinking water is, how would you use it and apply it and keep the system clean if, 5 miles down the pipe, there's no more residual. So those are some of the concerns right now. But, in reclaimed waters, you can have it. You have the residual there. The product is land use approved. You can take that reclaimed water, apply the PAA, and basically spray it on grass, spray it on golf courses, plants. So that's some of the advantages here. The peroxide will immediately be consumed or given off as oxygen, and the PAA will be gone, reverting back to acetic acid. So that's the safety of the product. It's land use approved. You can spray it directly on for reuse and reclaim, and that's exactly what they were doing in Milan on the orchards.
Alberto?
Yes, so on the reuse side, one of course needs to consider the Title 22, California Title 22 standard. And one of the things that one needs to demonstrate in order to get Title 22 is a 5-log reduction in polyvirus under certain conditions. And I think that while, as Bob mentioned, the product can be applied successfully and maintain bacterial control in a very effective way, I think more research and more data is required to assess, how exactly the virucidal side is going to work, especially when it comes to, getting Title 22 certification.
Thank you so much. And there were actually, both of you kind of addressed it, but there have been a number of questions on the application of peracetic acid into potable drinking water. If Alberto, if you could start and maybe address how that might move forward. And the one question essentially looked at taste and odor. So what sort of testing / work would need to be done to allow for PAA to be used in potable drinking water?
Absolutely. So, I mean, in order to apply PAA in drinking water, you got to have NSF 60, and I'm sure that we could do that. The question is, if you use PAA as a pre-oxidant upstream, kind of like replacing potassium permanganate or chlorine dioxide, other oxidants, the question is one of cost effectiveness. If you use or want to use PAA for disinfection of drinking water to protect the distribution system, then the disadvantage is that, as Bob mentioned, the advantage in this advantage is that you don't have a residual, because the concentration of the residual PAA will decay very quickly and turn into peracetic acid. So unless you have a situation where the distribution system or the average residence time in the distribution system is hours, you would have an issue of not being able to maintain a residual. So that's my perspective on that.
Bob, could you add some more to that?
Yeah, in drinking water, there's other concerns. When you're dealing with the residuals, at 1 part per million, I defy anyone to even sense the product at all. You're down so low, you don't see any impact on pH, so you don't see any of the residual. When you ask the question about the basin, there's no problem with any type of erosion, corrosion, acidity, because the concentration is so low that there's no pH change. Now, in drinking water, you've got other things to be informed with the current chlorine treatments. There's concerns about nitrosamines. Solvay is working with the University of Missouri to investigate that on a 3-year grant that's been issued. And also, Solvay is funding with the labs in Cincinnati and the US EPA to do more drinking water tests and do complete virus pathogen studies. So right now, it could be used in drinking water, but it's going to be a long uphill fight based on how the regulators try and control it. The chlorine's grandfathered. You smell it, you taste it, you know it's there. But again, it's going to be a very difficult road to hoe, I believe.
Thank you so much. There's another question. This relates back to, we talked a little bit about toxicity and safety issue. If there were to be a spill of PAA at a wastewater treatment plant, how would that potentially impact the activated sludge biology? I'll let Bob start with that one, and we'll ask Alberto.
Well, typically the containment won't allow it to even come within the sludge area. Yes, it works on recycling and maintaining filamentous bacteria, so it would have a logical impact on the sludge if you had the concentrated product. When you put it in a bulk application, you keep it isolated. You have containment, 1.5 times the volume. So you're building that into the process. Leaks typically won't happen because the lines will go on the outside of the building, going directly to the application point. So you're potential for leaks into the sludge or the system or even areas you don't want it are going to be minimized. But you would feed it very similar to bleach and recycling sludge if you do have a filamentous or a bulking or foaming issue.
Alberto?
Well, not much to add. Just that if there's a spill, it has to be dealt with through dilution. But as Bob said, the chemical needs to be maintained in containment. So the likelihood of having a spill that would affect biological process is very low.
Thank you so much. Glebra, another question for you. If you could reiterate the amount of PAA per gallon you're using per MGD of flow, or what you've used over the last year. There was a question on that.
Yes, we're currently dosing 1.91 parts per million, and we have a calculation that we do that allows us to figure out what that set point is, and that set point is the number of million gallons, the amount of peracetic acid per million gallons of flow. So we're at 11 gallons of PAA per million gallons of flow right now. And like I said, that was at 1.91 parts per million. We have dosed as high as 4.5 parts per million, so it could be 25 gallons, 26 gallons. But right now at the 11 gallons is pretty much where we want to be.
And an additional question for you. You showed your break-even point. Could you address at that point what you were paying for hypochlorite and what you were paying for PAA at that point in time?
I don't have those numbers off the top of my head. I would have to do some research and go into our billing program to get those numbers for you.
Okay. This is a question for Alberto and then probably related back to Bob. Within your presentation, Alberto, you talked about impacts of PAA and BOD, and the question was, in those comparisons, did you look at the difference between soluble and suspended BOD, and can you address the correlations you did see relative to that difference in effluent quality as it impacted PAA use?
Right. So the overall impact of TOC, TSS, or BOD is that it creates a demand for any oxidant, right? So the higher these values, the higher the demand for PAA will be, and therefore the higher the dose would need to be to achieve disinfection. Because of the acetic acid component on peracetic acid, you do have a contribution to BOD. But at the same time, as mentioned before by both Bob and I, there is you're adding oxygen as well. So the net impact is on BOD by adding PAA is rather negligible. I don't know if that addressed the question, Gary.
Well, let's let Bob try and tackle it, and maybe I'll restate it.
What I've seen here, it's very logical that any organic materials, any live materials, or your BOD or suspended solids, you will have consumption of PAA. It's not the PAA that's being consumed, though. The peroxide is reacting with those materials and reacting with the organics that are there, and that's what's being consumed. It shifts the equilibrium, so you see PAA drop. Okay, so as you measure PAA, don't believe the PAA is basically saying, oh boy, it's being consumed. The equilibrium is what's being consumed. The peroxide is what's driving the reaction. So in places you have high TSS, places you have high BOD that are incoming, take a look at how you feed sacrificially. What's the least expensive method to achieve that background or break point before you actually let the PAA, which is the expensive part of the program, do its job. So there's keys we're looking at right now in 3 applications where we're looking at sacrificial feeds to overcome that. Now, another thing I'd like to say on the discharge is that we've demonstrated the fact by using the test at Steubenville going from PAA to to bleach back to the PAA, we saw absolutely zero change in discharge CBOD. Again, we're down to 0.3 to 0.4 parts per million discharge. You won't see it. We found in Florida that approximately 1 part of PA residual would contribute 1 part per million of the CBOD. So again, it's a rule of thumb. It's not an absolute number. It'll change based on the locations, but you will see an increase based on the residual. But again, you are contributing oxygen too, so you know what's balancing what out. But just remember, though, the peroxide is an active part when you have slime layers, when you have TSS that have organics involved with it.
Thank you so much. I'm going to just maybe readdress, because I think it came up a couple of times, relative to toxicity issues with PAA. Are there any known byproducts that we would be generating relative to the addition, similar to chlorine, if we add PAA? And I'll start with Bob, if you could.
I can pull a chart up here. If you want to start with Alberto, I'll pull a chart up and tell you exactly what's produced.
Okay. Alberto, if you could maybe start off with that.
Other than the products of decomposition of the peracetic acid, there's no known disinfection byproducts from this process. And I'm sure the chart Bob is going to pull up is that of the decomposition of peracetic acid.
No,
right?
well, no. I'm looking at the peracetic acid. What's interesting here is that you will have organic acids. You'll see trace amounts, almost non-detectable amounts of organic acids, which makes sense. I mean, you've got acetic acid as a building block for other organic acids.
Correct.
That's all you'll see.
It's a product of decomposition of peracetic acid.
Yeah, so you do have that there, but it's also a food source. I mean, so you're taking a look at some of the comparables that are going to the water. There's no THMs, there's no carcinogenics, there's no mutagenics, and if you try and test PAA, which everyone's, oh, we're afraid of PAA, you can't test it after 10 to 15 seconds. So that's what we have to change the mindset of when we discharge in the streams. What are we limiting here? If you can't test it, you know it's not in the water after 10 to 15 seconds. Where, do we put discharge basins in? Do we change our discharge? There's a lot of questions that are starting to come up that I'm asking, regulators. Okay, how do we look at this differently? So those are some things that I'm looking at with how we change the rules and how you can fit it so that it doesn't impact the environment. One thing I'd like to bring up, though, that maybe people don't know is that the product's been in the U.S. since the 1950s. It's spread on asparagus, broccoli, apples before they go to market. So it's already been in the food industry and used on products as they go to market. So it's not a foreign substance that has just been introduced into the municipal area. It's finding that it can be used. But it's already been used in food. Again, because it dissipates, it reverts back to acetic acid. They consider it safe for consumption.
Thank you so much, Bob. I think we'll just end with one final question, and this is probably going to be addressed to both Bob and Alberto. This is your last 30-second type of thing. There's been a number of questions relative to PAA and its use in stormwater, CSOs, advanced primary treatment. Do you have any experience / thoughts on the application of PAA in that instance? Bob, can you go first?
Yeah, I did a lot of CSO work early. We're going to be doing 3 extensive studies here this spring. There's some very distinct things you have to be aware of in CSOs: the solids, the hydrograph, the flows, the pHs, because you could have varying pHs anywhere from 7 to 8. So you have to understand the dynamics of what's coming in. Part of that is that the suspended solids are very interesting on the ash contents versus the organic contents. All right, and finding out what that driver is. That will tell you what your background is and what you have to overcome. Stormwater is very similar. You have more floatables. You don't have the high solids. You may be in lower solids levels. But on CSOs, you may get up to 1,500 to 3,000 parts per million of solids. So you definitely have an issue there you have to overcome. Are there ways to automate it? There may be. But again, I think we're right at the beginning on trying to understand the mechanisms that occur in CSOs.
Okay, and Alberto, for your last comment here before we wrap up, we're at time. So
no, I'll be brief. Peracetic acid is a great solution for both CSO and primary applications. We're conducting trials in Pennsylvania on CSO, in California for primary, very effective, can go and oxidize things that are not necessarily oxidized by chlorine, very effective with particle-associated bacteria, and a number of benefits for PAA in these two applications. We'll invite everybody in the audience to reach out to us and discuss these applications in the future.
With that, we'd like to thank everyone for tuning in to this webinar on the use of peracetic acid. Based on what I'm seeing, it was very well attended. We appreciate your comments and your questions, and we'll look forward to answering all of those in the next couple of weeks. And with that, I'll return it back to Rebecca.